I'm live now. So there's going to be besides today's lesson, folks, which again is going to focus totally on the antiderivatives. Some formulas will derive here, and they're going to be all very easy. So no big deal, really. So besides these formulas, what you need moving forward, you will need a technique called the U substitution in our book, or a change of variable in the integral, and that's pretty much going to be it for the semester, for the rest of the semester. So we don't have much stuff to cover in terms of in terms of depth. We will still cover smaller things here and there that would help you. Some of them again are applied questions that might help you in other classes, maybe non-math classes. And then some of them will help you in calculus too. But just remember, just so you all know, and if you need some advising before you register to in calculus too, I can offer you some pointers again, because there's a significant gap between where calculus 1 ends and where calculus 2 starts. And in a situation like yours here, where you take calculus 1, in the spring, there's also the added problem of the summer break, which tends to be long. That's when people forget the stuff, and then in the fall, instead of starting here, where you're expected to start a little higher, people start actually a lot lower than where they finish calculus 1. So that creates a problem there. And, there's instructors who would want to, put in the effort to cover that gap. But then there would be instructors who would expect you to, be sharp from day one, and know your things very well, do the review of trigonometry, which is needed for calculus 2, and it's actually not even done in calculus 1, it's done in pre-calculus. So it's a bit of a complex process, and succeeding in calculus 2 is probably one of the big challenges that our students face here in our program. Okay, so that being said, today's lesson. So let's get to today's lesson. Today's lesson will be about antiderivatives, and today we're going to discuss formulas. So yesterday we said in words that we kind of spend time on understanding the logic of calculating antiderivatives. So when the derivative of a function is another function, we can read things in reverse, and we can say that the antiderivative of a result is the function I started with. All right, so today we're going to calculate formulas, because in the end, you need to know formulas. You know the definition, fine, but get the formulas. And that's what we're going to focus on today. Now, most of these questions that I do here after you watch the video, and again, I saw activity online, so there's probably people who prefer to stay home and watch these videos after the class, which is fine. But when you watch these videos, so pause where I say, here we solve this problem. I state the problem on the whiteboard, pause the video, try to solve the problem yourself, and then run the video and see how the problem was done in class. So that's the only way, folks, to learn the stuff, to check that you actually know how to do the things that we do here. And even if you don't know, that's fine, but just understand that the process, the simple process of thinking of a problem, trying to solve a problem, is actually the main step towards understanding the subject. Because if you don't know, at least you figure out what you don't know. So I don't know how to accomplish this step, how to get from here to here. Let's see how he did that in class, and you can check and see how I did that in class. And then that's the process of learning. So I'm an idealist, but I hope that you do that, folks, when you study. That's really going to serve you very well. So please do follow my advice here. All right. So that being said, okay, let's go to our business here is very much concrete about so again, we're still at 3.9 anti-derivatives, and we're talking about formulas. So today we do formulas. And let's see, the first thing that comes to mind, so when you calculate the derivative of a function, for instance, x to the 10 prime is 10 x to the 9. And we said yesterday that we read this as the antiderivative. So if we want to read with antiderivative language, because this is really a language that we're learning here, the antiderivative of 10x to the 9 is x to the 10. But how about if somebody asks, what is the antiderivative of just x to the 9? Why should I worry about this coefficient 10? Because usually, like you ask what's the derivative of x to the 9, you can very well ask the other question, what's the antiderivative of x to the 9? And it's not difficult, folks. So when you calculate the antiderivative, fortunately, this process is linear in the constant that you use there, in the sense that if the antiderivative of 10x to the 9 is x to the 10, if I want the antiderivative of x to the 9, I can use proportionality, and I can say, so 10x to the 9 was x to the 10. For x to the 9, I would say 1 over 10. So divide x to the 10 by 10, right? So by this 10 from here. So 1 over 10 x to the 10. And is it true that that's the case? Yes, actually it is true. So 1 over 10 x to the 10 prime is the same as 1 over 10 times, and then you do the derivative of x to the 10, which is 10x to the 9. And that 10 cancels out, and we end up indeed with x to the 9. So there we go. The antiderivative of x to the 9 is 1 over 10 x to the 10. So that's the answer. And let's write it down nicely here. The antiderivative of x to the 9 is 1 over 10 times x to the 10. Excellent. So if that's the case, can we derive a general pattern? Can we do that the same thing in general for, maybe not necessarily x to the 10, but let's say, let's do another example, kind of try to figure out the pattern here. Let's say we do x to the 8. We want the antiderivative of x to the 8. Hold on a second. So let me write on the other board because there's not much room here. So we want the antiderivative of x to the 8. So what did we do for x to the 9? We wrote that as 10x to the 9, and that we knew. So for x to the 8, it would be natural to look at 9x to the 8. And maybe we want to find out about the antiderivative of 9x to the 8. So what would the antiderivative of 9x to the 8 be? Well, that will be x to the 9 because, I know very easily that x to the 9 primed is 9x to the 8. So with the same logic as before, I can say, oh, then the antiderivative of x to the 8 will just go by dividing the entire thing by 9. So indeed, the antiderivative of x to the 8 is 1 over 9 x to the 9, because, you know, for 9x to the 8, I have x to the 9. So for x to the 8 itself, I would have 1 over 9 x to the 9. All right, so we got that. We got the antiderivative of x to the 8 being 1 over 9 x to the 9. And the antiderivative, let me just put here, and the antiderivative of x to the 9 we found earlier to be, you know, the antiderivative of x to the 9, or 1 over 10 x to the 10. So what do we notice here? If you carefully look at these examples here, you will notice, folks, there is some sort of a pattern, and that pattern is not difficult to discover. So again, I'm pretty sure that if you calculate a few more derivatives and do the exact same process where you divide by the coefficient to get the corresponding antiderivative, what you will get is the antiderivative of x to the n of x to the n is, and you will see that what you need to do here, so you really need to go up 1 with the exponent. You see x to the 8 goes x to the 9, x to the 9 goes x to the 10. So which is not surprising, because it's the, if you want, the inverse process of taking derivatives. So if derivatives, you know, you lower your exponent by 1, of course, the antiderivatives, you will increase your exponent by 1. So would be something like this, x to the n plus first. But again, that needs to be adjusted. So so that needs to be adjusted where you would say, oh, okay, so I have x to the n plus first. I need to adjust this thing here with a constant 1 over n plus first. Why is this constant over here? Well, because if I just did the derivative of x to the n plus first, I would get n plus 1 times x to the n. So if I divide out by that, I'll get this thing over here. So that is the antiderivative of x to the n. All right. And it's 1 over n plus 1 x to the n plus 1. And this is a formula. This is the fundamental formula that we want to remember here, folks. I'm going to write it again on the next board. So, so key formula here for the antiderivative of x to the n. And I can put n here, by the way. I'll discuss about n a little bit. So n could be any integer really, or any rational number if you can think of, if you want, even real number. We didn't do those. But what you want to be careful here, you want to be careful with one issue. So n could not be -1. I'll show you why in a second. So so anyway, the key formula for the antiderivative of x to the n, so we'll say here antiderivative of x to the n is 1 over n plus 1 times x to the n plus first. All right, so this is the antiderivative of x to the n, and that's the formula that you will always want to remember. So you know what, let me box that formula with a different color so everybody remembers that. All right, so I'll box this formula with red. So this red circle formula is the antiderivative of x to the n. So that's the one over here. All right, folks. So so now that being said, we are almost ready to set out and calculate a bunch of antiderivatives. But before we do that, let's derive some, let's make some comments here. So as I said, n has got to be, could be any number other than -1. Why would n not make sense at -1? Well, that's because of this, you know, denominator that you would get here. 1 over n plus 1 would be 0. And that's the antiderivative we're talking about. So we're talking about the antiderivative of x to the -1. Now, in physics or in our classes, x to the negative 1 is, people call it 1 over x. It's 1 over x. It is what that's what it is, 1 over x. So we have 1 over x here, and we're saying that in this class, we will not learn a formula for the antiderivative of 1 over x, because that doesn't fit the subject the way we develop it here. In Calculus 2, however, you will get the necessary tools to actually learn what the antiderivative of 1 over x is. And I can tell you right now that that is the natural log of x. So in Calculus 2, you will learn about that. In Calc 1, however, we are going to assume that n is never equal to negative 1. And if you run into a problem where you have to find the antiderivative of x to the negative 1, that probably is by mistake. Or if it's a real problem, and indeed you end up doing that, you end up having to do that, the antiderivative of x to the negative 1, you're just going to say, well, you know what, it's the natural log of x. That teacher told me, but I'm going to learn it in Calc 2. All right, for those of you who take Calculus 2. So that is the antiderivative of x to the n. Now, the next thing that I want to do here is a bunch of antiderivatives for some trig functions. Nothing very intelligent, really. It's just spelling out what we get when we write the derivatives of the trig functions. So just spelling out those things, it's going to be 3 formulas that I'm going to write here. They're very easy formulas. So let's go to the next page so we don't mix them up. All right, so we know from trigonometry, I mean, we could write several, but we learned that left side, remember there was a table, and here it says function, sorry about that, folks. All right, so the table was, let me write this down a little lower here. So the table was something like this, function derivative. And that was one half of the table, and then there was the second half, and there was function and derivative. So that's a derivative here. And in this table, you had sine x, cosine x, and tangent x on this side of the table, on the left side. So this was in the book. And then you had secant x, cosecant x, CSE, and cotangent x, and you had derivatives here. And I said, you know what, these derivatives, you can always look them up in books. You don't have to memorize. For example, the derivative of secant is secant tangent and things like that. I don't expect memorization in this class for the right side of a table, because again, it's very sophisticated, well, not sophisticated, let's say very artsy in a way that we don't use those in, I doubt that you will ever see those in practice, and even in calculus too, occasionally here and there, but they're not going to be all over the place to the point where you cannot live without having those memorized. So you can always look them up in a book. Now there's, again, instructors and instructors. Maybe your instructor is more, more aggressive towards, having these memorized and such. And you can, if you just have a book, the same book, you just memorize these things here and you move on with, if you need those in calculus. But I doubt you will need them with any sort of frequency. So maybe an occasional use in a now and then. Now for sine, cosine, and tangent, the story is different. These are very useful and they are used very often in practice, much more often than these on the right side. So these you need to know, have them memorized. So again, my principle is minimal memorization, but the stuff that you memorize, you really need to know. So cosine x is the derivative of sine, negative sine x is the derivative of cosine, and for tangent is All right, so you have secant squared x, and I said that in calculus too, you will also need this one plus tangent squared x, but we don't even use this in the calc one. So this is just I tell you that it existed, but we never use this thing. Even in the book, you don't use that. All right, so these here need to be well understood. Well, there's a similar situation now with antiderivatives. Now, remember when you do antiderivatives, all you do is read things the opposite way. So over here, you would say that going the opposite way with antiderivatives. All right, so that means I'm going to write here quickly the antiderivative of cosine x is going to be sine x. As you can see in the table, you have the derivative of sine is cosine. The antiderivative of negative sine x is cosine x. The antiderivative of secant squared x is tangent x. So folks, again, I have these memorized on the right side, but I'm not gonna push you to memorize anything there because you know they're less useful. These here, however, very useful. Now, the only thing that I would want to change slightly here in this writing that I did, you know, you have the antiderivative of cosine, which is sine. Over here, the second row, the antiderivative of negative sine is cosine. Why would I have to worry about negative sine? Let's say the antiderivative of sine. What should I do? Well, the exact same thing that I did earlier. I should divide by -1, and I could say, you know what? The antiderivative of sine is going to be negative cosine. So with that being said, we can recreate the table over here, at least the one on the left side, because I'm not going to do the one on the right side. We can recreate this table to talk about antiderivatives right now. And I'm going to put those three formulas over here, and I'm not going to put them as a table or anything. I'm just going to line them up under each other. So I'm going to say the antiderivative of let's start with sine because we always have, for whatever reason, people like to start with sine of sine x is, and we said if you look back in the table, so sine was the second one, here was negative cosine x. The antiderivative of cosine x is sine x. Again, look back to in your table, cosine x is sine x over here. And the antiderivative of secant squared x is tangent x. And you know what? Like I did earlier, oops, second, let me select the new color. Like I did earlier, I am going to circle these with red again. These are key formulas. So key formulas, make sure you have them well understood and memorized. Now, as a couple of pointers, so there's a couple of pointers over here that I could give you, and we should perhaps talk about those first. So, folks, remember there is a distinction between derivative and antiderivative, and unfortunately, people need to get not need, they tend to get confused sometimes. And they say, oh, so the antiderivatives really work pretty much like derivatives for trig functions. The answer is no. The antiderivatives, notice how they are always different from the derivatives, folks. So for instance, the derivative of sine is cosine, but the antiderivative of sine is negative cosine. So this is key here. It's a small difference. It might look small, oh, but but if you memorize the derivatives correctly, you will know that the antiderivatives have different signs for sine and cosine. So the antiderivative of sine is negative cosine. The antiderivative of cosine is sine. The derivative of cosine is negative sine. So we have minus cosine for sine x. For cosine x, we have positive sine x for the antiderivative. And secant squared is tangent. Now, you might wonder, oh, wait a second, you cheated us here. So you didn't tell us the antiderivative of tangent. Well, unfortunately, I cannot tell you that now here in calculus 1 because that is a calculus 2 problem. So in calculus 2, you will learn the antiderivative of tangent, which is which has to do with so it's I can tell you what that is. It's natural log of cosine, but it has to do with the substitution method, and then you have to learn that antiderivative of x to the negative 1. So it's a combination of techniques to get to that. It's not that simple. But you can so over here we really don't have the exact correspondent of this table. See here you have derivatives of sine, cosine, and tangent. Over here you don't have a derivative of sine, cosine, and tangent. You have the derivative and the antiderivative of sine, cosine, and secant squared. So these are the derivatives that we learn, folks, the key derivatives that we learn from trigonometry, for trigonometry in calculus 1. All right, so that being said, with these formulas in our bag of tools, what else is left there before we can actually solve problems? Well, before we can actually solve problems, by the way, folks, even in the book, they don't give more than these in terms of trigonometry. They give the antiderivative of secant tangent, which is secant. But I wouldn't worry much about that because in practice, I doubt you will see that very often either. So I'm just going to be happy with this here. So I'll make some comments now about the way to calculate antiderivatives in general, to combine things, right? So what we did here, we built the bricks. So we have a bricks for our construction. Right now we need to show you how to combine these things, these bricks, to actually build a wall and eventually build a big building. So the way to do that, folks, is by using some basic rules for antiderivatives. And these rules parallel the ones for derivatives. Remember, for derivatives, you have things like f plus g prime equals f prime plus g prime, right? So all right. So derivatives are here. Now, if you do antiderivatives, then the antiderivative of a function plus the antiderivative of another function is the antiderivative of the sum, more or less. So if you pay attention here to this rule, now I'm going to delete this rule so I don't confuse anybody. And I'll say that the rule for antiderivatives, an antiderivative of f plus an antiderivative of a function g is going to give you an antiderivative of f plus g. In other words, to find an antiderivative for the sum of two functions, you can focus on every single one of them and just add up the results. Likewise, folks, the antiderivative, and I'm just going to write this quickly, and I don't have just enough time to do some applications. Antiderivative of say some constant times f, like let's say 3f, is 3 times an antiderivative of f. So if you calculate if you want to calculate an antiderivative of 3f, you want to calculate an antiderivative of f and multiply that by 3, and that's going to give you a good result. Now remember that we said there's several antiderivatives, so I got to be a little careful here. But if you understood these rules as stated, then we should have no problem to calculate several complex antiderivatives. So let's go in the book and let's do some applications. Before we get to those applications, though, let me so right now we're ready to do applications. So let me point out one quick thing here. So back to the formula with the antiderivative of x to the n. Remember that that is, according to our formula, 1 over n plus 1, x to the n plus first. Okay, so that formula is valid, again, for all sorts of numbers other than -1. For example, if I want the antiderivative of something like x to the -3, what I'm going to say, look here, so let's look at the pattern that we described above. So I'm concerned first with the exponent. The new exponent has got to be the current one and plus 1. So the old exponent is now -3. The new exponent will be -3 plus 1, which is -2. And what I get here is 1 over -3 plus 1, right? Which is 1 over -2. So in simple terms, what I'm doing when I calculate the antiderivative, I'm increasing the exponent. So I get this new exponent, and then I say 1 over the new exponent. So I flip over the new exponent and I say 1 over that here as the adjusting constant. So that's what everybody should understand. And likewise, for another example, which is traditional antiderivative of x to the let's say x to the 1/2. Which function has a derivative of x to the 1/2? Well, according to my rules, I have to go x to the 1/2 plus 1 over here, and I'll have to say 1 over that, 1 over 1/2 plus 1. Now these numbers over here simplify a tad bit, so the number here is, 1/2 plus 1 is 3/2, 1 over that is 2/3, so you flip it over, times x to the 3/2 over here, folks. So this is the result. So what people do in practice, they usually calculate the new exponent, simplify that to the point where it's like this, and then they take that, flip it over, and put it in front of a function. So that is a trick, if you want, a computational trick to remember quickly how to do antiderivatives like that. And I'm going to start here, and I'm going to do a bunch of calculations from the book. So find the most general antiderivative. Now, when he says find the most general antiderivative, as I told you, the antiderivative of say x squared is, we found that to be, so we go to x cubed, so it's going to be 1/3 x cubed, right, folks? All right, so 1/3 x cubed, but we said that that's not the only function whose derivative is x squared. If you add a constant here, and people like to add this constant for reasons that I'll explain a little later, it has to do with physics, initial velocity or differential equations, it's important to find an initial value. So if you add this constant, you will still get a function whose derivative is x squared. And this format, 1/3 x cubed plus a constant, that's called the most general antiderivative of a function. Now, if you fancy throwing out the constant, I'm going to be fine with that. In Calc 1, that is not going to be necessary with one exception, which I'm going to point out later. However, in Calc 2, this is going to be a little problematic if you don't use that constant. So remember that the most general antiderivative is whatever formula you get here plus a constant. Of course, this is the main bulk. So this is your main formula, this one here, to which you add a constant. So you still need to get that. I mean, on a test problem, there's not going to be antiderivatives on this test, but on the test problem, on the next test, of course, I care much about this. This is going to be 8 out of 10 points or 9 out of 10 points. But, you know, don't forget, the most general is still with plus a constant here. So don't forget that constant. So if you fancy of maybe throwing out the constant, you can all the way to the last step of your calculation. And when you're done and you think you got the main result, just add a constant to that. All right. So in the book, problem 1 says find the most general antiderivative of, that's 329. Okay, of 4x, f of x equals 4x plus 7. Well, so let's see. The antiderivative of 4x will be 4 times, right, 1/2 x squared, because this is the antiderivative of x, plus, and the antiderivative of 7 is 7 times 1, so the antiderivative of 1 is x, so this is going to be 7x. Or you can easily see that 7x prime is 7. All right, so the result will be 4 times 1/2 is 2x squared plus 7x plus a constant. And that is my final answer. This is the most general antiderivative for 4x plus 7. Problem 2. By the way, folks, this is a point where you want to stop your video, look at these problems in the book yourself, try to solve them, and then copy the answers. So I mean, then keep rolling the video and running the video and seeing how that is done. F of x equals, in this case, x squared minus 3x plus 2. Again, all these problems are to find antiderivatives. All right, so that's the antiderivative. Again, 4x squared, we have x cubed times 1/3, right, folks? For minus 3x is minus 3 times the antiderivative of x is 1/2 x squared. And for 2 is 2 times x. So this is going to be plus c. In other words, the formula is 1/3 x cubed minus 3/2 x squared plus 2x plus c. All right, so this is the antiderivative. Problem 3. I'm going to do a couple more problems here. Problem 3 of section 3.9. F of x, again, the antiderivative we need to find here, 2x cubed minus 2/3 x squared plus 5x. All right, so the problem here is the antiderivative is 2 times over here for x cubed 1/4 x to the 4 minus 2/3 times for x squared. The antiderivative is 1/3 x cubed, and for 5x, 5 times the antiderivative of x is 1/2 x squared plus a constant c. So this is 1/2 x to the 4 minus 2/9 x cubed plus 5/2 x squared plus c. All right, there's the antiderivative. And finally, number 4, 3.9, and this is where I'm going to finish up our lesson today. You know what? So let me do problem 5 instead of 4, folks. I'll do problem 5 here, and then we'll do sorry about that. Let's erase here. So problem 5 is f of x is x times 12x plus 8. How do we do the antiderivative of that? Well, so we're going to apply a little bit of a trick here. So first of all, let's, again, there is no such thing as a product rule for antiderivatives. In fact, there is something related to the product rule, which is called integration by parts. You will do that in calculus too, but we don't do that here. So basically, the only option you have right now is to write this product as a bunch of powers of x. 12x squared plus 8x. And then apply the strategy that you applied earlier, antiderivative. Well, 12 times 1/3 x cubed plus 8 times 1/2 x squared. And that is going to end up being 4x cubed plus 4x squared. All right, so this is the antiderivative. If you want, you can add, let me do that, maybe add a constant c here. Again, for calc 1, this is not a big crime if you miss the constant here. And that is the answer for this particular problem. And I'm going to finish up the lesson here, folks. I'm not going to push any more. We have just a couple more minutes, but there's no reason to push it any more problems because it will be very different ones. So we'll do more sophisticated problems tomorrow. So again, I'm insisting on learning these things really well, folks. This is your foundation for antiderivatives, integrals, and everything else that follows. And really, I'm spending this time here to make sure that everybody truly understands these things and does these problems. So I'm going to stop the video here. As I said, I'm not going to do anything else today. And